Okay, section 4.1, functions of several variables. So this topic should be short and simple, I hope. So um, we have we've already begun to work with these things. If you look back on the topic of quadratic surfaces, I kind of immediately started to mention functions of more than one variable. Because that's what quadratic surfaces are, or at least that's what some of them were. But now we are formally defining these things. So, okay. So a function of two variables is something that looks like this. We have f taking in two inputs, x and y, and some output, which we may call z. And this maps a point in two-dimensional space in R2 to a real number, z. And, well, function being a function, you can define the notion of a domain and a range of the function in the same way that you would with functions of one variable, right? The domain is the possible inputs that you can give a function that would make sense for that function, and the range is the possible outputs that the function can produce. And so here we have an example. So suppose you have some function g of x and y that looks like such, and you're asked to find the domain and range of this function. So the range is the easier thing to determine just by looking at this. So we can get, because of the square root, we know that we can't get any negative numbers to come out. So then you might ask, well, can we get 0 to come out? And the answer is yes. If we make, say, make x equal to 2, y equal to 0, so then you end up with 16 minus 4 times 4, minus 16, and then minus 0. So you get 16 minus 16 inside, you get 0. So we do have a possible input that will give us 0. And then for the maximum, what is the highest thing we can get? Well, these two quantities are always going to be positive, well, before we take the negative. So the fact that x is being squared and y is being squared means that these terms will be positive until we take until we subtract them. So what is the smallest value that we can subtract from 16? The smallest value would be 0, um, which would make this square root into the square root of 16, which would make it 4. Oh, okay, so that's a typo. That should be 4. 4. Okay, I'll just upload it like this. Okay, so the maximum that you get is 4 the square root of 16 when x and y are both 0. Okay. Oh, so yeah, wait. Okay, so I do have it there, but I don't have it there. That's fine. Okay, now for domain. So the domain is harder to express in this case. So you're used to domain of a function being like, say, a union of intervals on the number line. Well, because we're now talking about functions whose inputs are in R2, or in two-dimensional space, the domain of a function is going to be a subset of R2. And that may be hard to express, as you can see in this example. So the restriction that we have for the domain is given by the square root function. We know that for the square root function to make any sense, the quantity inside the square root needs to be greater than or equal to 0. That produces this inequality. And then all we can really do to this is move things around and try to simplify it a little bit, but we'll only end up with this. Okay. And so the point is that this is how we would define the domain of the function. We can't do any better, really. What you can do is to depict what that domain looks like, which is what I do below. So one thing you can spot about this is that this does define an ellipse. So to make it match the format for an ellipse that you're familiar with, you'd probably want to make the right-hand side equal to 1, which means that you would end up dividing by 16 everywhere. So that would end up giving you x squared over 4 plus y squared over 16 is, we can say less than or equal to 1. Okay, so this is the standard form of an ellipse. This would be like, say, a squared, that would be b squared, and so a squared measures how far you extend in the x-axis. So you extend a far, which would be 2. So you can see that 2 and minus 2 are how far you extend along this x-axis. And then the square root of 16 is 4, so along the y-axis you extend 4 and minus 4. So from that, you can trace out the ellipse. And then the inequality, the fact that it's less than or equal to 1, means that you're shading inside the ellipse. If this was greater than or equal to 1, you'd be shading outside of the ellipse. And of course, the equals means that we include the boundary. We include the ellipse itself, the boundary of the ellipse. Right. So that is the domain for this function. It's defined by this inequality, or pictorially, we can say it's this shaded region. Right. Now for some ideas that we want to have in order to then be able to do things with three-dimensional functions that are defined with three variables. So first of all, the graph of a function of two variables defines a surface. And a surface, mathematically speaking, is a two-dimensional object which we're going to think of it as living in three-dimensional space. It can live in higher spaces, but we're only going to concern ourselves with three-dimensional space. So the fact that we use the word surface means we're talking about a two-dimensional object. So the analogy is with, say, a curve. A curve is a one-dimensional object, which might live in two-dimensional space or three-dimensional space. A surface is a two-dimensional object, which may live in three-dimensional space or higher. You kind of could also... I mean, you could say it can live in two-dimensional space, but that may seem a bit weird. It'll just be a subspace of it, subset of it. Okay, and so now here's some pictures of what the graph of a function of two variables looks like. So these are the kinds of things that we kind of already introduced in passing with the quadric surfaces, especially this one, this paraboloid. So you'll notice that our input space is the base, right? The x and y forms our input space. We can pass in inputs in x and y into our function, and we get back out a third quantity, this z, which we end up using as our height of our point in space. And so the graph of the function ends up being this thing that sits in three-dimensional space. But locally, right, on the graph itself of the function, this geometric object is two-dimensional. If I'm a point that is on this graph, I can only see two directions of travel. I can maybe see an up-down travel, and I can see a left-right kind of direction of travel. I guess same with this half sphere. So yeah, you can move along this like y direction or along this x direction. But by being forced to live on that space, we're not really able to move in the z direction directly. If we move in the z direction, we would leave the space, which is not something we're allowed to do as being a point that is fixed in the space. So these shapes are intrinsically two-dimensional objects. Okay. All right. I think that's all I want to say about that. So next, we have this other notion, a level curve. And I think we have trace as well. We should have trace, yes. Right, I guess I left it under the same heading. That's fine. So what is a level curve? So for a function of two variables, a level curve is what you do is you take your function and you set it equal to some constant. This constant is going to be you're going to have a particular value in mind, and you're going to want to actually set it equal to that. And then from that, you can graph what that looks like. So here's an example of this. I don't know if that's exactly, yeah. So this function, or these level curves, are actually level curves of this surface. So notice what we end up doing here is, without speaking about the level curves, we end up having an object that is two-dimensional. Once we impose this additional restriction, once we set the function equal to some constant, that decreases the dimension down by 1. It decreases the dimension down by 1, so that instead of a surface, we end up with curves. Okay, the particular curve depending on what the value c is. Right, so c equals 0, we end up getting this bottommost circle, and then as c increases, we end up kind of moving up. You can actually also think of these level curves as being horizontal slices. It's like you're slicing this surface with planes that are parallel to the xy plane at different heights. That's what the c actually represents. It's the z height. You're slicing that object at particular values of z. Okay. And yes, these a graph with various level curves is sometimes called a contour map. So in the real world, you may have seen like say altitude maps of like mountain ranges or something like that, or perhaps I think there's things like isothermals, kinds of graphs involving like weather and noticing like when do you have all the temperatures being the same. That kind of tells you like how wind is traveling. So so we have these kinds of objects that show up pretty much in the natural sciences. These things that are contour maps. Okay. Right. So that is one way of slicing, basically. And I'm sort of trying to connect vertical traces with contour maps. They're very similar. It's just that the direction that you're slicing is different. So we have this other thing called a vertical trace. Um, Level curves are always graphed in the XY plane because you're slicing parallel to the XY plane. But vertical traces, you are slicing in such a way that you either have an XZ plane or a YZ plane. Now, how does the vertical trace work? Well, given a function of two variables, what you do is you set either x to be a constant or you set y to be a constant. So I'm picking a and b as my constants here, and I'm either setting x, the input x, variable x to be a constant, or I'm setting the input variable y to be a constant. And then we end up with this kind of equation. So you'll notice that you have y as an input, as a free-ranging input, and z as some output. Then you can graph that. This is a function a function of y with output z, a function of x with output z. So this guy ends up living in the yz plane. This guy lives in the xz plane. And you can see that these are also slices of your surface, right, in these below pictures. So when we set y to be a constant, so this is the bottom bullet. If you set y to be a constant here, you end up getting slices that are parallel to the YZ plane. Is that the YZ plane? Hmm. Y is a constant. No, so it should be XZ plane. Yeah, okay, XZ plane. Right. And if you set x to be a constant, then you end up with these slices. And so you are parallel to the YZ plane. Um, and so the reason that they're called vertical traces is simply because these planes that you're intersecting with are vertical, right? The contour maps, the planes that you're intersecting are kind of horizontal. They're parallel to the XY plane. All right. So, an exercise. So I tried to come up with something different. Uh, I don't know how different necessarily, but so you're given a function, and then you're given specific values c. Now I just to make like a pretty picture, I used a lot more values c than I needed to. I think you are only asked to do like 2 values of c for your problem. Um, you're asked to graph them. Yes. So if I didn't do this with software, because it's actually very easy to do with software. In a sense, I cheated. But what you would have to do is like sort of think about this guy algebraically, I guess. So I'm just factoring the x out, and then this ends up telling me two things. Either for example, for c equals 0 for this trace or not this level curve. Um, if I was looking specifically at c equals 0, after factoring, I get this. So this tells me that either x is equal to 0 or y is equal to 1. Maybe I should say or here, just to make it abundantly clear. X is equal to 0 or y is equal to 1. And so that ends up giving you this level curve that is in green. So it's the degenerate hyperbola. If instead, let me just choose another one. I guess I'll pick the purple one. So that's this one with c equals 2. So x times y minus 1 is equal to 2, right? Well, this one's a little bit more... how do I do this one? divided by x and then add 1. So I'm just solving for y to make it look like a function. So 2 divided by x plus 1, right? And then if you just think about what the graph of this looks like, well, it has a a vertical asymptote at 0, which you could definitely mark. And then as it goes to infinity, you end up with a horizontal asymptote at 1. Is that right? Yeah, you do get horizontal asymptotes at 1. And then you could plug in specific points in order to make the sketch of it look accurate. But you know that this is a hyperbola with horizontal asymptote. By letting like x go to infinity, you can see that the horizontal asymptote is at y equals 1, and the vertical asymptote is at x is equal to 0. That together kind of would allow you to sketch this approximately, and to tell like which of the quadrants it's in. So just by picking a point, say x equals 1, you could figure out that it's in the first and third. These aren't quite the quadrants, but for these two quadrants as opposed to the other ones. That would the other ones show up because you have c being negative, right? Okay. So yeah, I think that's clear at this point. Now, how do we connect this? So we end up needing these ideas particularly for functions of more than 2 variables. So the point is that it's not really possible to completely visualize a function of 3 variables, right? So a function of 3 variables takes in 3 inputs and it gives you back 1 output. So the totality of that function, the graph of that function, would require 4 dimensions to see it completely. 3 dimensions of input, like 3 dimensions in our base and 1 dimension as the output. That output dimension has to be perpendicular to 3 input dimensions, the 3 spatial input dimensions. So that whole thing is in 4-dimensional space. That's not something we can really deal with. So instead, we take cross sections of it in order to be able to visualize it. And I guess the most useful cross sections to take are the ones that correspond to the idea of a level curve. But because we're up 1 more dimension, it's no longer a level curve, it's actually a level surface, which is kind of the other thing I'm trying to emphasize here, right? So with functions of 2 variables, the whole thing, the geometric object was a surface. When you take a cross section, you go down a dimension from a surface to a curve. So a function of 3 variables, you have, well, I guess the I'm hesitating. It's not really a volume or a hypersurface. I don't feel like either of those is fully correct in terms of terminology. But that object it's a 3-dimensional object living in 4-dimensional space. Because the inputs can vary in 3 dimensions, that geometric object, which you can't really visualize, it's a 3-dimensional object living in 4-dimensional space. When you take the cross section of it, that brings you down a dimension, bringing you down to 2-dimensional, bringing you down to a 2-dimensional object living in a 3-dimensional space, aka it is a surface. And so we end up with the notion of a level surface for a function of 3 variables. Level surfaces look like the following: you give a function of 3 variables, and you specify a particular constant that it should be, and you can try to graph it yourself. In real life, it's probably more sensible to plug it into software and have the software render what the thing looks like. But I guess for simple problems, you should be able to deduce what it is by kind of looking at the function. I think that in your exercise, I don't know if there's more than one exercise, but in your exercise, the functions of 3 variables they all correspond to quadric surfaces. So you might need to look back on those expressions to be able to identify what quadric surface you're working with. But they'll be particularly nice level surfaces. And I mean, I could go on an excursion and show you some really weird looking level surfaces. There are definitely those things in. You could look up like the word minimal surface, and you'll see some very interesting looking objects. But let's get back to this example, and I think this is the last thing to talk about here. So So we have this function of three variables, and the problem asks to find the level surfaces and describe them. So I kind of changed this up from the way that your problem is set up. Your problem actually gives you a specific constant. I sort of generalized it to be like, for any value c, what does this thing look like? And the textbook helpfully kind of, I just tried to modify an example in the textbook. The textbook gave for particular values c, 0, 1, 2, and 3, that this is what this function ends up looking like. And you can see that, well, what we're doing is we set this thing equal to that constant, right? Now, if that constant were, and maybe also just to make this look a little bit closer to the quadric surfaces, let's do it like this, right? That it doesn't look very helpful, but one, right? So if you kind of look through the quadric surfaces, you'll recognize this is like a squared, b squared, and c squared. The fact that you have 1 minus means you're talking about a, so say that we set this guy equal to 1 on the right-hand side, then this would be a one-sheeted hyperboloid. Okay, and then if this was equal to 0, this would be an elliptic cone. And then the odd thing is that if this was negative, a negative value, what you could do is multiply the whole thing through by a -1, and then the value becomes positive here, but then on the other side you end up with two negatives, which brings you to the case where you have a hyperboloid of two sheets. So that's actually another way to see that the one-sheeted hyperboloid and the two-sheeted hyperboloid are related to each other. It's just based on changing this parameter past the value 0. Once we switch from positives to negatives, we go from one sheet to two sheet. And so I mentioned that in this set of bullets, right? So at c equals 0, we end up with this picture where it's an elliptic cone. C greater than 0 are actually just all of these. And c is less than 0. I didn't bother to depict that, but it's a two-sheet hyperboloid. You can imagine it's kind of, it's like sitting inside. You could think the two sheets are sitting inside. Actually, you can kind of stack all of these inside of each other. You can nest them inside of each other. It's another way of thinking about these level surfaces, because they're cutting out points in 3 space where the value of the function is the same. Okay, I think that's all I have to say about this topic. So I guess that's it.